Welcome everyone, and thank you for attending part 2 of our webinar series, Smart Building, Driving Resilience, Efficiency, and Change, hosted by Scott Smith, Industry Principal at OSIsoft. My name is Tom Trappell, and I'll be your moderator. And today our guest speaker is Dr. Eoin O'Driscoll, Critical Infrastructure Protection Practice Lead from DSA. Today's webinar will take roughly 45 minutes, followed by 10 to 15 minutes of Q&A. But before we get started, I'd like to mention a few housekeeping notes. This webinar is being recorded, and we will be providing the recording and slides after the webinar. You can expect an email with the recording following the conclusion of this event. And finally, you'll notice on the right our Q&A option on the WebEx digital event platform. I want to encourage everyone to submit any questions you may have through this feature. If we're not able to get to everyone's question, we will certainly follow up with a response afterward. And with that, I would like to now hand it off to Scott Smith to get started with our discussion today. But gentlemen, thank you both for joining us.
Thank you, Tom. And I want to thank everyone for being here today and taking about 45 minutes of your busy schedules. Welcome to the second of 5 episodes on identifying driving value for facilities. Today, we have Dr. Eoin O'Driscoll from DSA providing some of their insights and experiences in this presentation, I will share a framework in which facilities can leverage value from the data available within the facility. The challenge with what is being promised within the industry is this concept of smart facility or smart technology. But a smart facility does not deliver a return on investment alone. It's about how you make that smart technology actually deliver specific value. The focus today is learning from others' experience, but we have just a quick message from your sponsor. Software is an enabling technology like a tool in your tool bag. If used properly, we help support your objectives by translating data into actions. One consideration in selecting a product is that facilities provide similar functions, temperatures, pressures, electric delivery services, but they all use different technologies, different assets, and have different problems. And you need a platform or data infrastructure that is agnostic to and supportive of all of these different platforms. OSIsoft is about the deriving value from the data from IoT sensors, assets, plant SCADA systems, building automation systems, and third-party data sources such as your utility and weather services. We have been at the data infrastructure game for about 40 years and have a breadth of experience in understanding critical operations and how to drive value. Now on with today's presentation. 3 lessons I hope you will see today. One is the challenge of all of the disparate systems and how to harness the data before it overruns your capability to make it valuable. 2, one key tool he will share is about using a framework to make sense of the data through repeatable templates. And 3rd is the data collection is just the starting point, making sure you have high quality data to allow for a baseline of operations, but also to ensure machine learning and how you will learn to solve for the data gaps and poor data quality. I would like to offer you, please feel free to ask questions at any point during this presentation today, and we will also have a Q&A session at the end. Eoin, over to you.
Thank you, Scott, and thank you, Tom. Good morning, everybody. My name is Eoin O'Driscoll, and I work for DSA, where I'm the practice lead for critical infrastructure protection. DSA is an employee-owned IT consultancy company headquartered in Trevose, Pennsylvania, and we've been working with federal, state, and commercial clients for over 57 years. Within critical infrastructure protection, we use the PI system to improve the resilience and effectiveness of critical systems. And one of our most notable customers is the Nuclear Regulatory Commission, or the NRC, where we've operated and maintained the emergency response data system for more than 12 years. And that system, called ERDS, requires the collection of data from each of the commercial reactors across the US to a central platform, and it's a project that we're very proud of at DSA. My personal background, I'm a mechanical engineer, a graduate of Trinity College Dublin in Ireland, and I completed my PhD with Johnson & Johnson, and my research was really at the intersection of mechanical engineering and statistics, and I focused on the application of machine learning to improve the energy performance of a large manufacturing facility. Over the last 10 years since then, I've worked in engineering roles at companies ranging from very small consultancy firms all the way up to multinational organizations like J&J and Siemens. And I also did spend 2 happy years working at the Guinness Brewery power plant at St. James's Gate in Dublin. My goal for this webinar is to demonstrate some of the ways facilities data can be used to improve operational efficiency. So at DSA, we operate PI systems for customers like the NRC, Sandia National Lab, the University of Maryland, amongst others. And I'll be sharing value propositions today from an end user's perspective to really showcase the value of a data-driven approach to smarter facilities. Okay, and this first slide is really the foundation for everything I'm going to share during the webinar, and it outlines the approach we take to situational awareness and operational intelligence in the facility space. So starting from the left-hand side, you'll see a lot of the typical systems in the facility space, so metering systems, control systems here. This could be a building automation system or a SCADA system to control a central plant. Certain assets like some pumps or lift stations maybe aren't integrated directly to a system and operate on their own. We have diagnostic systems listed here, and one example I'll come back to later is with vibration data. Databases here refers to maintenance management systems and really any other business systems that relate to facilities management. And then finally, we have geospatial information systems, or GIS. And what the PI system allows us to do is to collect all of the critical data from all of those isolated systems and bring it into a centralized operational data warehouse. And at that point, we claim we have situational awareness. So there's nothing really new has happened to the data. There's no new instruments installed in the field, but we've brought all of the data to one central location. The next column then is calculate, and that's when we deploy analytics ranging from simple to very sophisticated to that operational data warehouse to provide operational intelligence. So what I have listed here is logic-based FDD rules. That's something we'll come back to and is becoming more and more prevalent in the industry. There's very simple comparisons against industry best practices, standards from NIST, ASHRAE, and ISO standards, and then finally, machine learning. So when we bring big data together, there's a lot of value can be gleaned from that information, but we need more sophisticated techniques. So things like multivariate regression analysis, genetic algorithms, neural networks, and even moving towards AI is all possible with the data in a central framework within the PI system. The next column then is visualize and notify. So now we've brought the data to one place, we've layered analytics on top, but we need to make sure that the new information and the intelligence makes its way to the appropriate people at the appropriate time. And that's what the visualizations and notifications are for. And then finally, the outcomes. And we'll touch on each of these during this morning's webinar: our improved facility operations, condition-based maintenance, load management, anomaly notifications, and then finally, the overarching goal is enhanced infrastructure resilience. To make this all more secure, we have the bottom bar you can see, and that is that cybersecurity monitoring allows us to continuously assess the status of each server that hosts a facility system. So are the latest software versions installed? Are all of the recommended patches installed? Are all of the communicating ports managed correctly? And this allows us to continuously manage the risk profile of this new integrated and smarter facilities infrastructure. So that's really the overarching framework, I would say. And the main takeaway from this slide is that there's a lot of systems, there's a lot of data, and there's typically very little integration. And data infrastructure solutions like the PI system allow end users to integrate data from all these standalone systems into one time series optimized database. And then finally, layering analytics on top of this data set provides operational intelligence and a more data-driven facilities operation. So the first application I want to talk through is related to electrical distribution across a multi-building campus. And in this case, it's the University of Maryland's College Park campus. The image here is just making the point that electrical distribution is complicated, and important data related to this distribution exists in various isolated systems. So we have PDUs, or primary power distribution units, that have their own monitoring systems. If you have on-site generation, a local SCADA will house the data for any of that information. Automatic transfer switches and uninterruptible power supply data lives typically in building automation systems. And then finally, there's often a standalone power monitoring system that contains consumption and power quality data from electric meters and submeters all across the campus. So this was the challenge at the University of Maryland, and it was further complicated by the fact they had no remote monitoring capabilities for many of these systems when they had a grid outage in 2016. And in total, the utility grid was down for about 90 minutes, but the campus itself ended up being down for longer. And that's because they didn't have complete transparency into the distribution of electricity across the campus. So working with the university and with OSIsoft, we deployed the PI system to provide situational awareness into this distribution. And the next 3 slides are going to show what this looks like in place now. The first screen here is the campus level operational status of the primary grid feeders on the top line, the CHP feeds on the bottom line, and then each of the primary cubicles in between. And all of this real-time data provides a quick summary of the high-level status across the campus. The data is built within PI and visualized in PI Vision so it can be accessed remotely. And the traffic light color coding clearly communicates the critical information to the system operators. So it's very easy to tell what cubicles are closed, what are open, and where there may be challenges just from this quick screen that summarizes a lot of information from different systems. The next step is moving from the high-level look to within an individual feeder. So now we can see the status of each building again in real time. So you can see high-level summary statistics are included. We've got kW, power factor, current draw, voltages, and this screen continues to provide the information required to troubleshoot any electrical issues on the campus. So if an electrical outage was to occur, there are notifications built into these screens to immediately notify all of the appropriate utilities and engineering stakeholders. And before this was installed, as was the case in 2016, one of the most time-consuming tasks when responding to any outage is collecting and sharing information. Finding out what buildings don't have power and communicating this information to the right people all takes time. And with the PI system and the integration that I'm showing here, all of this data gathering and communication is automatically handled through analytics and notifications, and that gives your maintenance teams a heads up or a head start on restoring power. And then the reason I have the smartphone illustrated on this screen is just to show that all of this information can be accessed from the field using a smart device, a phone or a tablet. Within the PI Systems manual logger, engineers at the University of Maryland make changes to represent actions they take in the field. So one good example on what's shown on the screen here is moving the location of an open point. So if an open point is going to be moved in the field, instead of having to notate it, take it down, bring it back to the facility space and enter it into the PI system, it can all just be done real time in the field, and that improves the efficiency of everybody involved. The final step of this project then was tracking the availability of power within each building, and that's what we'll look at on the next slide. All right, so now we started at the campus level, we moved to within a single feeder, and now we're at the building level. And here you can see we have real-time information on the status of the grid connection, the availability of emergency generator power, the status of each automatic transfer switch or ATS, and also the uninterruptible power supplies or UPSs. Again here, each component on this screen is continuously monitored so that the utility staff are notified if a generator is offline for any reason, if an ATS switch is in the wrong position, or when the battery life of any UPS goes low. And this level of end-to-end transparency into electrical distribution has improved the ability the university's ability to respond to outages and significantly reduce the downtime experienced when outages do occur. So going to build on that a little bit here. So the next example is connecting a different utility, this time chilled water, with a geospatial platform for campus-wide monitoring. And what you can see on this screen here, and you probably can't make out the text, and it's just really to illustrate the point. It's a standard engineering design drawing for distribution of chilled water across a campus. And again, here it is, the University of Maryland's College Park campus. So each building has design information for pressure drop, for flow, for delta T, but the design data rarely, if ever, represents actual operation. And this was another challenge we faced at the University of Maryland. So how do we operationalize these CAD drawings to make them digital and provide real-time chilled water system information? And this slide shows the integration that we all collaborated on and came up with. So this visual shows data taken from disparate systems. So we have SCADA system data for the chillers, and then we have building side information coming from multiple automation systems, all presented on an Esri interactive map, again, in real time. And this type of visualization is definitely a step change from what's traditionally available to facility managers when it comes to chilled water distribution. Before an integration like this, you'd have to go to the SCADA system, download a trend file. You'd have to go to the automation system, download a trend file, bring them to your desktop, get all the data to line up in Excel, make sure you don't have bad data, that the timestamps all align. And all of that data manipulation takes time and limits your effectiveness as an energy engineer, as an operator, or any other facility stakeholder. But with the integration through PI, all of that tedious data collection and scrubbing takes place within the system, and all you get is the data that you need in the format you need it in. So looking at the graph or the graphic on your screen, you can see we have the chilled water distribution lines color coded here. So blue for supply, red for return, and the legend on the left-hand side. And this is all flexible, so we can change this to be different colors, et cetera, et cetera. And we also have the building status listed. So green means that a building has chilled water flow, a red empty box means that it doesn't. And we can, with a GIS platform like this, a true GIS platform, we can build layers on top of this. So now let's say we really care about low delta T. So now I can have a layer that shows the delta T at each building. I can show the delta P at each building in a separate layer, and I can create new color-coded notifications on top of this graph to show where I have problems. So it's very flexible, and it's all built upon the fact we have that structured data within PI. And an interesting aside with this project is the first time we presented this to the university, when we came to this screen, one of the facility managers sort of stopped us and said, is this live data, or is this just like more of a demonstration to show what it could look like? And once we said, no, this is live, they left the meeting because there was an issue with one of the loops that they weren't aware of. And to me, that story really highlights the value of an integration like this and all facility systems integration. And that is that you really can't assess the complete operation of a large system unless you have all the data in one place. And then the last point to highlight on this slide before I move on is that it is interactive. So I can click on the different buttons and get different information. And the next slide I show is going to be a drill down from this main map to an individual building. And I would complete that by, like I said, just clicking on one of the buildings itself. All right, so now on this screen, we've sort of come from the geospatial landing page, and now we're looking at the data for chilled water consumption at a single building. And this screen it's a template. So we have the key parameters listed: outside air temperature, relative humidity, flow rates, consumptions, and valve positions. And the value of this screen being a template is that we only build it one time, and then because of the structure of data within the PI system, it will automatically populate with data from each building. So if you think about that, if you've got 300 buildings and they all have chilled water supply from a central plant, and you want to see these 5 parameters for all buildings, you can templatize with the PI system, build that screen once, and then it will just automatically, it's not quite automatic, there's a little bit of work to make it push across all of those additional screens. And what that does is it eliminates one of the expensive services that you can typically, or are typically provided by automation system vendors, which is the creation of graphics. So using templates is a very efficient and cost-effective way to create visualizations. And with this data, going back to the 2 concepts that I introduced initially, we now have situational awareness. So we've got all the data in one place, but the next step is operational intelligence. So how do we get more value from this data now that it all is in PI? And continuing to use the example on this slide, we know and we can see that there's a correlation between chilled water consumption, temperature, and humidity. So we build analytics within PI to model these relationships. And once we build the models, we can compare current consumption against our model prediction and create an alert if there's non-standard consumption. So right now on this screen, there's an outdoor air temperature of 75 degrees, relative humidity is 54%, and the chilled water consumption is 330 tons per hour. So now let's say next week or in 2 weeks, the same environmental conditions exist, the same level of occupancy exists, but now all of a sudden it's 500 tons per hour. Well, that's something I want to be alerted to because it means that there's a step change in how this building is consuming chilled water. And if you don't have this information now and you aren't monitoring it, then how do you find out when there is an issue? How do you identify major passing valves or underground leaks? It can be, and I would argue maybe it is impossible without analyzing this data. And one thing that I come across when I present this approach is I'll get a response and someone will say, sure, that might work if you don't have network issues or sensor issues or you don't have 15-year-old meters. But the true reality is that no building or campus has perfect data quality, but you can still gain the benefits of analytics as you improve data quality. And I want to talk about some data enrichment approaches that help with that over the next few slides, because we're not just going to assume that everything is perfect and all data is perfect data quality, because it isn't. So now on this next slide, again, it's real data from a different campus. So we have steam consumption now, and that data is coming from an automation system, and then there's temperature data coming from the National Weather Service, usually from a local airport. So on the left-hand side is steam consumption, right-hand side is outside air temperature, and then on the x-axis it's time. So the correlation between outside air temperature and steam consumption here is pretty clear. As temperature rises, steam consumption falls, but you'll see a data gap around January 15th where there's a straight line. And this is the standard response from most automation systems when a meter loses connectivity. And you might be lucky in your facility that you may have meters that have onboard storage, but that's typically only for a short period of time. And if you don't, that missing data is gone and can never be recovered. So on the last slide, I talked about using analytics and building on top of the correlations we can see. But if there's a straight line like this, it's going to cause a problem, because now I see a temperature rise on January 15th, but I don't see a steam consumption drop. And if I do have a model running on this data, it's going to trigger a false positive. So the question becomes, how do we fill this gap? And in certain cases, if it's a short outage, the industry standard is less than a couple of hours. Straight line interpolation, like you can see here, is a pretty good guess. It's as good a guess as any. But in this example, we're missing almost a week. So this straight line, the straight line is not going to work. So what do we do? Well, the best approach we can take here to improve data quality is to leverage the known correlation between the two variables. And we do that with regression analysis. So in the call-out box here, you'll see I've just got the standard form of a regression equation listed, as well as the coefficient of determination, or R squared value. So the R squared value, if you're not familiar, it's a way to quantify the level of correlation between two variables. So in this case here, it's saying 81% of the variation in steam consumption is caused by changing temperature. And that's a pretty strong correlation and one we can use to estimate the missing steam consumption because we continue to receive the temperature data from the National Weather Service.
Owen, we have a question that just came in. How does this differ from setting this up in a building automation system?
So there's a couple of different answers, I suppose. The first I would say is that in a lot of these implementations, it is a multi-building campus environment that's maybe grown over 20 or 30 years, and there isn't just a single building automation system. I would further that and say, in that case, you could build this in multiple automation systems, but then there's a lot of replication, a lot of redundant work, and it's not an effective way to deploy something like this. But within a single automation system for a single building, it's still different again because the ability to write analytics like this in a standard automation platform, the type of analytics you're actually able to use within a standard automation system don't match up to what you can do within the PI system. So in this example here, you could maybe do single variable or multivariable regression in automation systems. And in fact, I know you can, but you can't get to advanced analytics using your native automation system, at least not in their current form now.
Thank you, Owen.
No problem, no problem. So now you can see that, and actually this slide is a pretty nice segue on that, Tom, because what you'll see here is I have regression-based estimation requires strong correlation. So here, if we're going to look at chilled water consumption, there's a strong correlation with wet bulb temperature. If we're going to focus on steam consumption, there's a strong correlation between dry bulb temperature, and obviously in both cases, occupancy is important too. But let's say there isn't a strong correlation. What do we do? And one alternative I have listed is pattern matching. So for pattern matching, what we do is we look at the current time. We go back over a period of 2 months or 4 months or 6 months, whatever we decide is the right period of time. And we look at the same time of week, the same time of day, and then we'll make an estimation based on the average of all those profiles from historical data and apply it to the gap we currently have right now. And I can say pretty confidently that the majority of automation systems wouldn't be able to deploy pattern matching within the sort of locally hosted system that you have in a regular facilities management office. And then continuing on along with that, and still I guess related to the question that was posed, is what we can do with that model now that we have it. So here we've included 5-day forecast data. So now we're taking more data from the National Weather Service, which is connected into the PI system, and we're predicting consumption, and that allows us to make more informed decisions around equipment scheduling and maintenance planning. So instead of always being in a reactive mode, we're starting to get ahead of things because we have an idea of where we'll be over 3 to 5 days from now. An example would be if we see a forecast for unseasonably hot or cold weather, maybe we want to delay some of the scheduled maintenance on a chiller or a boiler just in case it's required.
Oh, and we have another question here. Is the regression-based estimation completely automated within the PI system platform, or does it require some human input?
Yeah, so that's a really good question again. And these aren't planted, but they're matching along pretty well with how I'm going here. So what I'm just about to talk about here is rolling baselines and how they can improve the forecast accuracy. So they are rolling baselines and it all occurs automatically. And what a rolling baseline does is it's a sliding window. So let's say we have, or we decide, end user decides they want to use 6 months of data or 12 months of data. Every day that moves forward, the analytics within the PI system will calculate a new baseline. So it's not a 2016 baseline or whatever year, which is the standard approach that we continue to compare our performance against. It's a rolling baseline that learns as the building evolves. So the building, any building from 2016 to now, it's changed. There is no exception pretty much there. So the rolling baselines that automatically calculate allow you to compare your current performance against the latest baseline information for that building, so you're always getting the most accurate comparison. Okay, so I'm going to switch away from, just change gears a little bit here, and switch away from data quality and talk about data-driven maintenance. And the integration I'm going to show here connects automation system data, diagnostic system data, and a maintenance management system. But before I go into that example, I just wanted to quickly go over the most common maintenance approaches here. So starting off with the least complex, we have reactive, which is a break fix. So here, think about an air handling unit, the fan belt breaks, your static pressure drops, and then the phone starts to ring because people are really hot or really cold in their offices. The result is always unscheduled downtime, and it's the least mature maintenance practice. The next up is preventative or time-based. This is almost ubiquitous across the industry. So we're looking at changing an air handling air filter every 6 months, or we're going to service an air compressor after 1,000 hours. And what happens with time-based preventative maintenance is that many components are changed and maintained before they need to be. Those recommended service intervals are based on average data for thousands of similar systems that manufacturer created, and it's not tailored to your asset, how it was installed, or how it's been operated since it was installed. And then the last, and what we're going to talk about here, is a more predictive approach that is data-driven and based on the actual condition of your asset. All right, so this example, what you can see on the screen, it's taken from a research facility in Cleveland, Ohio. The air handler is serving a critical research base, and the goal was to avoid unscheduled downtime wherever possible. There was some pretty tight temperature and humidity requirements in the space where the experiment was occurring, and if it went outside that window, they had to restart the experiment, and there was a significant cost to the customer. To increase the reliability of this overall experiment, I guess, a condition-based maintenance project was deployed, and part of the project included monitoring vibration signatures. So on the left-hand side, you can see just the air handler itself. In the center, you can see the fan motor, the fan belt, and the fan itself. And you can also see 2 vibration probes, and they have the little orange caps on top. And there's one on the motor itself, there's one on the bearing that you can see at the near side, and there's a third vibration sensor on the far side, the second bearing of the fan shaft. And then on the right-hand side, we have the acceptable limits for vibration velocity. So these come from a number of different sources. This here is from ANSI. You can also get it from ISO, and there's, like I said, different organizations that have standards for vibration velocity limits in rotating machines. But by monitoring the vibration signals, referencing these standards, we were able to create a spectrum of acceptable vibration velocities specific to this air handler. So continuously monitoring these vibration signals provides advanced warning, and that's the key. It's advanced warning of any electrical or mechanical issues that need to be addressed. And on the next slide, I'm going to introduce some actual data from that project. All right, so now it's a line graph. It's from the air handler on the previous screen. On the left-hand side, it's fan speed. On the right-hand side, we have the bearing vibrations. And from the analytics in place, we identified a shaft alignment issue that was causing excessive wear on the bearings. And you can see that there's a step change between the level of vibration between the two bearings. And over time, this issue would have persisted and eventually caused a period of unscheduled downtime. But with the integration of the automation system data, here shown as the fan speed, the diagnostic system data, here being the bearing vibrations, and then connecting all of this to a maintenance management system, a ticket was automatically generated to schedule maintenance work and address the issue. So this data-driven approach to maintenance paired with the systems integration helped support the facilities group at this research facility achieve their goal of maximizing uptime. And now I'm going to move into fault detection and talk about an application here. So in my opinion, no webinar on data-driven approaches in this space, in the facility space, will be complete without covering fault detection. It's become a very powerful and popular analysis tool with huge libraries of rules, but there's limited or maybe even no standardization within the industry. And at a previous job, I spent about 3 years designing and deploying FDD projects across the US. And the number one piece of information I want to share with everybody online today is that just because there are thousands of rules doesn't mean you should apply thousands of rules, and your initial system design is critical. It's been my experience that a small subset of the rules deliver 80% or more of the value of fault detection. So looking at the air handler here, and it's really just to represent fault detection, but there are hundreds of different rules available for an air handling unit like this. We've got return air, exhaust air, outside air, dampers, coils, fan, and some other sensors. So there's literally hundreds of different rules we could apply to an air handling unit like this, but we really don't need to. And I'm just going to talk to you some of the rules that are valuable, and then maybe some of the rules that are less valuable, just to illustrate and demonstrate that fact. So the first would be the operation of the economizer is critical, is absolutely critical, and would be the number one component of any air handler that you need to continuously monitor. So if you have a 100% open outside air damper in summer, it's very expensive. It can be extremely expensive. What happens is you're bringing in very warm, very humid outside air. You're forcing your cooling coil to do as much work as it can, but it still can't get the supply air temperature to set point. And what happens in the space is the terminal boxes or the VAV units that are connected to the air handler, they want more cooling, so they open their dampers. When they open their dampers, the static pressure in the air handling unit will drop, so the fan speed will increase. Eventually what happens is your fan speed is at 100%, the unit's working as hard as it possibly can, but it still can't meet the supply air temperature set point, and that's because it's bringing in 100% outside air. So that's just a way to never meet the needs, always have comfort calls, and spend a lot of money because one single component isn't operating the way it should be. Then the sort of inverse of that is if you've got an outside air damper that's 100% closed, then maybe that's a safety issue because there's no ventilation, and that can all be handled with a couple of targeted analytics at the economizer operation. The next one I would want included in all fault detection systems would be simultaneous heating and cooling. Again, it wastes a lot of energy and reduces the overall capacity of your system. But then there's a lot of rules that exist in libraries that aren't really valuable. So one example there would be any logic that checks for small temperature deviations from the temperature set points. So for example, if supply air temperature isn't within 2 degrees of set point, that's a rule that you can apply, but is it valuable? I don't really think so. And if you walk through the analytic, the temperature probes installed in an air handler, when they're installed, are probably accurate to about plus or minus 1 degree, and they drift over time. They're almost never maintained. So what that means is that there's a strong chance you're going to start creating faults that reflect sensor accuracy and not the true operation of the system. But even if the sensors were perfectly accurate to a fraction of a degree, do you still want to ask somebody to go and troubleshoot why your supply air temperature is 57 degrees instead of 55? And I think the answer to that question is no. So I think the summary for fault detection just is that there's too many rules out there, and applying too many results in a tremendous amount of faults that are hard to navigate, and that reduces the overall effectiveness of any fault detection system. So the key is to only select high impact rules that eliminate noise in the system and maximize the value of your fault detection deployment, and using the PI system to connect the outputs of a fault detection system or fault detection built within PI to a maintenance management system allows the high probability, and I'm emphasizing that, the high probability rules to automatically trigger ticket creation, and this is extremely powerful. And then the last bullet I have on the right-hand side is closing the loop. And that's when an analytics platform automatically makes changes to the automation system to correct errors. So before it was we were going to create a fault and then generate a ticket, and that is useful and valuable. But there's also a way to close the loop where a fault can trigger a platform to make a change to your automation system. This obviously isn't possible for all faults. If you have a broken damper linkage, an analytics platform can work all day and it's not going to be able to fix that. Someone needs to physically go repair or replace the linkage. But the last two examples I want to focus on are going to cover applications where closing the loop is possible. All right, so I'm going to talk quickly here about scheduling. So scheduling projects are one of the most cost-effective improvement measures within the facility space. I spent many years doing Azure Level 2 audits, and I'd say in 95% of the reports I created, I made a recommendation to improve scheduling. And the most common approach to HVAC scheduling is still to manually enter schedules within the automation system to cover standard business hours. So in an office, it might be 5 a.m. to 9 p.m., Monday to Friday with reduced hours over the weekend. And in some cases, you might have holidays programmed, but that really is the standard approach. The issue with an approach like this is that the program schedule is an estimate to cover sort of worst case, and it doesn't account for the actual schedules for any individual space. And over the last 5 or so years, more and more companies have started using cloud-hosted room reservation systems where maybe in a university setting, a professor goes in, reserves a room for a semester, or even for a standalone lecture, or maybe in an office setting, someone reserves a conference room. So the actual scheduling data for the spaces exists in an IT system, but there's no connection between these cloud calendars and the automation systems that control HVAC. And making the connection, and this is a broader statement, but making the connection between IT systems and OT systems is at the core of any smart building. And with the PI system, you can bridge this gap to automatically update HVAC schedules as building occupants interact with those online room reservation systems. And that's what I'll show on the next slide. So now here on the left-hand side, we had that IT silo of room reservation information. On the right-hand side, we had the automation system, but there was no connection. So now we're pulling that data from those cloud-hosted sources. We're bringing it through to the PI system, and then we're sending commands from the PI system to the automation system, and that's ones and zeros to the terminal boxes within the individual spaces to make them go occupied and unoccupied. And what we've seen with this approach is over 30% HVAC energy savings, and I think that's expected if you're familiar with how they're normally scheduled, how HVAC is normally scheduled. And then the last bullet point is that we've also worked to get this approach approved by a regional utility company. So under their monitoring-based commissioning incentive or rebate program, we've worked with them to have this methodology approved, and the rebate payments are 25 cents for every kilowatt hour saved over a 12-month period, as well as an upfront payment to cover a portion of the deployment costs. And this is a really powerful example of how connecting different systems can improve facilities operations and generate significant cost savings. And then the last application here, this is something that DSA and OSIsoft, we're currently trialing under 2 different federal government-sponsored proving ground programs. And it's a more holistic approach. It's a combination of many of the value propositions I've talked through so far in the webinar, but the primary purpose is electrical load management. So before we had fault detection, anomaly detection, but on top of that now we have analytics that forecast when to discharge thermal storage, to estimate how much energy a PV array is going to generate over the coming days. And there's also a novel dynamic load shed table. So the focus of the proving ground programs is to prove how we can deliver intelligent load management. And to us, that translated into meeting utility curtailment requirements while minimizing the impact to building occupants. And to do this, we built some pretty sophisticated dimensionality reduction and prioritization algorithms into the PI system. And I wanted to finish off the webinar talking about how this is achieved, because it's a unique and interesting application of advanced analytics. So to demonstrate how this approach works, I'm going to use air handling units as an example here. So we collect about 100 different data points from each air handler. It's standard tags or points, temperatures, static pressures, fan speeds, the return air CO2 concentrations, and any occupancy sensor data that's available from the space level. And we then push all of this data through a dimensionality reduction algorithm. In our case, we use PCA, or principal component analysis. And this takes a high dimensional data set, so 100 points in our case, and projects it onto a lower dimensional feature space. And that's what I've included here on this slide, just as a demonstration. So the best way to think about the 2D projection we have here is that it condenses the information stored within all of those 100 data points into 2 key variables, and they're called principal components. And that allows us to plot a simple XY chart like I have here. And then once we have this projection complete, we can evaluate which air handling units are the best candidates to have temperature deadbands expanded, to be shut down early, based off of the level of criticality. And that level of criticality comes out from the principal component analysis and how far each of those air handlers ends up from the critical center, which is notated by that red mark in the middle. So this is definitely a novel way of leveraging data to create a more connected and smart building that optimizes its own energy performance, and that's through the fault detection and closing the loop. But it can also adjust to the needs of the utility grid it's connected to, and that's via the intelligent load management. And that's everything I wanted to share in the webinar. I know I definitely covered a lot of ground there, but I do look forward to answering any questions that you have. And at this point, I'll hand it back over to Tom and Scott.
Thank you, Owen. At this time, folks, we'll be taking questions from the audience. Once again, please use the Q&A option to the right of your WebEx interface, and we'll answer your questions as they arrive. If you've happened to change your view to full screen, you may find the Q&A option located at the bottom. All right, let's see if we have some questions coming in. Okay, great. Owen, what is the best way to securely get data from your local systems?
Okay, that's a good question. So there's a couple of different ways to get data securely from the automation systems installed locally behind firewalls to the cloud, if that's what you desire. It doesn't have to be the way this is deployed. One is, I would say, the standard with firewall exceptions. That's, I think, an industry standard. But there's also a more secure way, and that's through data diodes. And a data diode, or a unidirectional gateway, is a physical device that is built in such a way that it only has circuitry to allow data flow from the local asset to the enterprise level. So it's physically impossible for data to flow the opposite direction. So I would say that's the second option, and that definitely locks down those local networks. And just as a follow-on to that, one of the things that we do at DSA is cybersecurity assessments and penetration tests. So we'll actually come to a campus location or even just a standalone building and assess how secure the networks are within that system, how secure those individual servers that host your systems are, and really try and quantify your level of exposure from a cybersecurity standpoint. So that's something that that we also do along with the PI system integration work.
Excellent, thank you. Okay, our next question. What tools do you use to do PCA, and do you have any examples of insights or problems you detected with PCA?
Yeah, so we use a couple of different things. So Azure ML Studio is one. For local installations, we use Python. It's a open source scripting language. And PCA, challenges with PCA, that sounds like a separate 1 hour webinar, but yes, there are of course challenges with PCA. It's really a tool that we use for classification. So we try and build a way to use PCA that's going to tell us if something is critical or not. And I would sort of maybe just leave it at that one. So PCA is quite complicated, and I don't think it's not a good use of time right now, I don't think, to explain some of the in the weeds challenges with PCA, because there are many.
Thank you, Owen. Our next question, how does the utility benchmarking forecasting differentiate new baselines from anomalies?
So how does it benchmark from anomalies? So that's another good question. So the way that the two tools or the two analytics work in tandem is that as time moves forward, the baseline will update and compare current consumption, but anomalies have, I would say, different thresholds. So if we want to look at the number of standard deviations from the mean, or a different statistical approach at looking at a non-standard consumption versus a predicted model, the level of significance is different between an anomaly and moving forward our sliding window.
Great. Okay, our next question, can you provide an idea of effort required to recreate these analytic tools?
Yes, so I think the level of effort to create these analytic tools is, I would say there is a learning curve. It's somebody who's a mechanical engineer and is an expert in HVAC and automation systems. That doesn't necessarily mean that person will be able to script PCA, but the beauty of the PI system, again, is that there are templates built. So we already have a lot of templates built for PCA. We have some feed-forward neural networks built in using the PI system or connected to the PI system within Python. So there's a lot of different analytics that have already been built, and there's other people. It's not just DSA, or it's anyone that even has their own PI system and don't use integrators, have built their own analytics within the PI system. So I would say if you want to build from scratch, there's a significant level of effort, a pretty big or steep learning curve, but you don't really ever need to build from scratch within the PI system, because a lot of people have covered a lot of ground before.
Great, thank you. Does the analytics and integration also optimize chiller plant optimization?
Another very good question. Yes, so it can. So one of the things that happened, and I believe it was the focus of the first part of the focus in the first webinar in this series, is that PI can be used to collect all of the information you'd need for that optimization. So for chilled water systems, the standard metric is kW per ton. So you collect all of the power consumption information from each of the chilled water system components. That's your towers, your pumps, your chillers, as well as the amount of cooling provided in tons. And then what the PI system can do, or through analytics, is what's called a constrained optimization. The constraint is that you're trying to minimize kW per ton, and there's obviously limits to what you can do with the individual components, so you can't turn a fan to 150%, for example. So it's called a constrained optimization, and the analytic will process through all of the different combinations and permutations possible for the components that you've put into the analytic, and it will tell you the optimal operating point. And that's something that can be done with the PI system. It's not something we have done before. So we have done the analytics to identify when your current kW per ton is higher than what your kW per ton could be, but that's not a place where we've closed the loop.
Great, thank you. Our next question, how could this work for, say, an EOC?
An EOC is an acronym is not immediately coming to mind right now.
If you could respond with a little bit more detail, we can answer that question. Okay, I'm going to go, Emergency Operations Center.
Yeah.
Oh, okay, so an EOC, I'm familiar with, NOC is the one I go for, which is usually like a national operating center. So yeah, absolutely. I mean, this is this is perfect for an EOC or an NOC because usually with an EOC, you're looking at multiple different buildings. So you have, maybe it's a large bank and you've got a lot of different branches nationwide, and you're trying to see what the best performing buildings are, the worst performing buildings. So those basic energy management information system functions can be handled within PI, but then you can also build on top your fault detection and your more advanced analytics. So you can see what the number one issue that you have with air handlers. As another example here would be, let's say you always have filter issues. So if that's something that becomes obvious across your entire portfolio, then you can feed that back into sort of maintenance and training procedures so you can better equip the local guys, the guys in the field, of what to prioritize during maintenance based off of information that you're pulling from the data at an enterprise level.
Owen, can I add on to that? Do you have any experience based on our work from home under the current circumstances and how maybe this can support that model as it continues forward?
Yeah, definitely. So it's definitely been busy since this all started, and that's because if you think about it now, everybody that isn't essential is working from home. And when you're not working from home and you're at a university or you're in an office building, if you want to get information from an automation system and you're a sustainability professional or you're somebody else who's not working in it day by day, you can walk down the hall, go in, ask somebody for some help, or log in directly yourself. But you obviously can't do that right now. So having remote access to all of the local data is something that's, I would say, even more not desirable but necessary right now. And I think that's a trend that isn't going to reverse when this all passes.
Oh, and we have another question now. One of our operation challenges is we don't have enough automated metering. When is the appropriate time to start?
So the appropriate time to start is really as soon as you can. It definitely isn't it's not a sort of binary question. So you don't start performing analytics when you have perfect metering and perfect data quality, like I said earlier on, because that's a destination that you're probably never going to get to. But you can deploy targeted analytics. It doesn't have to be a comprehensive thing with neural networks and some of the more advanced things we've talked about here. You can just have a very simple analytics on your metering data that is advanced metering infrastructure, so that does come back to an automation system, and you can start there. So if you only have 10% of your meters that this type of analysis would make sense on, then start with the 10%, and then as you build out your metering and instrumentation infrastructure and more becomes available, you can just phase those in as you grow. So the answer isn't when you're done, the answer is now or yesterday, because there's a lot of value in that data, and if you're not looking at it now, you're more than likely missing opportunities to improve efficiency and save money as well.
Great, thank you. Folks, we're approaching the end of the hour, and it looks like there are no further questions. So I'd like to thank everyone for attending today's webinar. If you do happen to have additional questions following today, please feel free to reach out to us from one of the follow-up emails sent out afterward. Once again, thank you for attending. And Scott, do you want to give a preview for next week's episode?
Absolutely. And I want to reiterate what Tom said. There will be a survey going out that will allow you to check if you'd like to have a direct conversation with Owen. So please take a look at the survey, and you also have a chance to win a book from the author of episode 4 on high-performing buildings. Next week, we have University of California, Davis, discussing achieving savings through improved thermal energy storage dispatch and data science at UC Davis. So I hope you can join us next Tuesday as we walk through thermal storage and optimization of that data for data science. And I want to thank everyone for their time today.
Once again, thanks everyone, and we hope you have a wonderful rest of your day. And Owen, Scott, thanks again for joining us.
Thank you, Tom.
Thank you.
Take care, everyone.